Okay, we're back. And I've done a little work since we left off the last video there. So what happened was I was simulating the program that we had written so far. And what we're doing is we're adding this table of numbers, one number at a time, to the output compare register. These are signed 8-bit numbers. So if the most significant bit of the number is a 1, which it would be if the value is greater than 80 hex, then it is a negative number. So if you add the negative number, you're actually subtracting the number. Well, what we're doing is we're adding an 8-bit signed number to a 16-bit number in the 16-bit register. So if the most significant bit of our 8-bit number is a 1, then that indicates it's a negative number. Well, the other 8 bits on the upper byte of the number should all be 1s also to make it a negative number. So we need 8 1s in a high byte, and the most significant bit being a 1 in the low byte, and then whatever the value is in the remainder of the low byte to add a negative 16-bit number. So what we have to do is convert our number from an 8-bit signed number to a 16-bit signed number. And one way to do that is to check the most significant bit. And if it is set, we'll set all the bits in the high byte. If it's not set, then we'll clear the high byte. So, and you can see here, I wrote a couple of little functions to test this that I'm explaining to you. So it's just a temporary function. It's not going to be part of the real program, but we can use it to demonstrate what I was talking about, adding the signed number. And then I did an rcall function I added here to the name for our temporary function here. I converted the number 100 decimal, or actually I should say minus 100 decimal. So if you remember to do a subtraction, you can add a 2's complement of the number. So I took the number 64 hex, which is 100 decimal. I converted that to binary to get 01100100. I inverted all of those bits, and then I added 1 to the number. So when you invert all the bits, you get 1001 64, right? 01100. Okay, 1001 1011, right? Then when you add 1 to that, you get 1001 1100, which comes out to 9C. So we have 9C as the number we're adding, which is going to be the same thing as subtracting 100 from the number. So I created this function, and I've got an rjump to repeat this function over and over so you can watch it subtracting the values 100 decimal at a time. And you can convert the hex values to decimal if you want to verify. But right now we're starting at this point with a value of 1500 microseconds in PWM AH and AL. So we need to add the low byte of our number, and then we'll clear R17, which is the one I'm using temporarily. And then SBRC, skip if bit and register clear. So we're testing bit 7 in the register, in the temp register, and if it's cleared, we're going to just leave R17 as 0 and add with carry the PWM AH with 0. If it's not cleared, if it's a 1, then we're going to set all the bits in R17 to 1 and then add with carry R17. So that will do the proper subtraction from the number. And so what we need to do is take our function we originally wrote here and modify it a little bit to add this code that tests the most significant bit and converts it to a 16-bit number. And so I think what I want to do to start with is create, instead of using the name R17, we'll use the name temp H for a high byte. So I'm going to go up here to the top and define a name temp H as R17. Okay, temp H equals R17. And then when we recopy those names, this is an interrupt function. So what we should do is do a push temp and a push temp H, right? And then at the end, before we return, we want to pop those off in the reverse order that we pushed them. So we'll pop temp H and then pop temp. Okay, so now we want to, so we're going to load our LPM Z plus, whatever that value is. It could be a positive or a negative number. It's a signed number, right? So, and then we're going to add the value to PWM AL. So we've got that line already here. Add PWM AL temp. And then we're going to, so this is where it starts changing. I want to clear the high byte. So clear temp H. Okay. Then I want to do these lines of code here. And Control C, copy and paste those lines there. So then we're going to add with carry. Okay, so this is going to be temp H here, R17. Then add with carry temp H. And that should be all we need to do. Then we can store the value to the PWM, to the OCR registers. And so that should fix the value. So we're adding a signed value. I would recommend running it through a few times and simulating it. And so this code down here, you can write it, test it. When you're done with it, just comment this line out here. Stick a semicolon in front of that line if you want to, and then it won't run that code down there. So now, this is only for OCR1AH, so I'm going to assemble this. And we have no errors, so I'm going to start the simulation. Okay. Apparently I changed some code and broke a breakpoint somewhere. So, yeah, this breakpoint here is the one so I can disable that breakpoint. Or it's already disabled. Toggle breakpoint. No, it toggled the wrong breakpoint. That's alright. I should ignore it. Alright, so we're going to step down through. Oh, one other thing I forgot to mention. I added these two lines of code because we didn't load the value into the PWM AH, BH, AL, and BL. So I added these 4 lines of code, those 2 move instructions and these 2 move instructions, so that we're actually using R15 and 14 for the PWM-A and R13 and 12 for the PWM-B. So we've already verified all that code works, and so I'm going to set a breakpoint on the PWM update here, and then we'll run it full speed ahead to that breakpoint, and then we'll step through our code here. Okay, so we're at the beginning of the PWM update. We're going to push temp and temp H to the stack. Load program memory. So now you should load a 1D into the program memory, into temp. And you can see 1D is here in temp. Okay. And then it's going to add it to PWM AL, which is R14, so DC plus 1D. And that comes out to F9. And then we're going to clear the temp H, which is R17, it's already cleared. And skip if bit and register cleared, so it is cleared right now. Our temp is R16, so it skipped the set register. Add with carry, so that should be adding, the carry bit is cleared, so it's going to add 0. And store those to the OCR1A. Then we're going to compare. We should have a, it should do a no add reset because it's not there yet or even close. And then it goes back to main and waits for the next interrupt. So we could be doing this here all night, or okay, what I'm going to do is set a breakpoint here, which I already have set here. So this is at the end of the table, and I just want to, and it's going to take several seconds to run through and read this entire table, adding it to the OCR A register and OCR B. So I'm going to, let me see, how can we do this? This is OC1A, OC1B. So those are going to be on port B. And you see we have the pins configured as output pins. At our breakpoint, we're always going to be at the same. So unless we configured the output compare registers or enabled the interrupts on them, we won't see the changes on the port B output pins. We could enable the interrupt, and then even then, well, yeah, we can see the change if we enable the OCIE 1B and OCIE 1A interrupts, and then you could put the compare register and just a RETI, because the interrupt doesn't need to do anything. So so what we can do is add the OC1A ADDR and OC1B ADDR. OC1A ADDR, and here just do a RETI, and we'll set a breakpoint there. So okay, OC1A, OC1B ADDR, and then we need to set the bits in the OCIE 1A and 1B, and we're already enabling the TIMSK1 here. So what we can do is pipe and add the 1 at the OCIE 1A and OCIE 1B. And pipe and add a 1 shifted left by OCIE 1B. Okay, that'll enable those interrupts, and then we can set breakpoints at those interrupts. Toggle breakpoint there and a toggle breakpoint there, and we'll be able to simulate and see the timing on the interrupt as well as seeing the bits changing. So let's build that. Okay, and run it. And we've got 20 seconds left in this video, so I'll leave it to you to simulate it, test it, and run it to the breakpoints at full speed ahead and watch the pins on PB2 and PB3. And so we'll wrap this video up here for now. Email me if you have